In data centers, we often mention or use a technology that has extended beyond just data centers to potentially within our enterprise networks, where there is a similar application of this technology. This is called micro-segmentation. At the same time, we will also learn about another related technology called our business chain. These two are not particularly related, but both belong to some aspects of this business, like for instance, traffic routing or access control related technologies. So let's discuss them together. First, micro-segmentation by name. It's called micro-segmentation. In English, it's called micro-segmentation. It's interpreted from two perspectives. So hold on a moment. From two perspectives, we can interpret it. So the first perspective is what is segmentation. The most traditional way of segmentation is actually based on IP subnetting. For example, we have a 1.0 subnet and our 2.0 subnet. They are segmented from each other. In traditional enterprise networks or in non-data center scenarios or traditional data centers that are based on the subnets, we can implement this on layer 3 devices or on some layer 2 devices doing ACL-based filtering to determine if they can access each other. This is called segmentation. So what is micro-segmentation? As the name suggests, between 1.0 and 2.0, it's only based on a subnet for segmentation, which isn't detailed enough. Especially in data centers, particularly in cloud data center scenarios, our control requirements are very detailed, so the method of dividing by subnet is no longer suitable. Thus, we propose a more detailed method of segmentation. So how do we segment more finely? Do we use a single address, such as 1.1, 1.2, 1.3, to do this? Actually, that's not enough. It's not detailed enough. It can be based on basically anything you can think of. A lot of things can be used for segmentation. For example, separating two hosts or two servers belonging to different business departments. After segmentation, what then? Still, control is implemented to see if they can access each other. If they can, then access is allowed. If not, then access is not allowed. So, the essence is how to make a finer segmentation. Later, we will discuss another technology called our business chain. Later, we will mention another technology called our business chain. Mentioning it by name, you might not know what it's called. Let's take a look. It's called service function chains. First, let's see what the definition of service is. The definition of service, if you understand the carrier sector, you might know. In carrier networks, we often mention something called WAS. What is WAS? It's called value added service. What does value added mean? Actually, in the carrier industry definition, there are many definitions of this term. If you translate it into something we can easily understand more straightforwardly, you will find it's not as hard to understand as its name suggests. What is WAS? For example, the carriers, they will do. You need to use the carrier's network. We all know early on it involves PPPoE dial-up. There might be a modem, and that modem might not be a fiber modem. Early on, dial-up was used. At the time of dial-up, the carrier side would have a specific device dedicated to handling this dial-up called what? Called a bus device. Right, this device handles your dial-up. For carriers, it is a WAS, meaning you can understand it as something beyond just carrier services. For the carrier, it is a WAS, which means you can understand it as something beyond just the carrier, providing some devices beyond basic forwarding. For example, for a carrier, firewalls or devices specifically for NAT. All these are called WAS devices. What do they do? Beyond basic IP forwarding, apart from our routers and our switches, they provide handling of packets from layers 4 to 7. These can all be called WAS devices. WAS devices, right? So the final key point is what? Service, right? These devices all provide some service. So in the service chain, the first service refers to what? It's beyond the 1 to 4 layer forwarding. These devices from layers 4 to 7, providing individual handling from layers 4 to 7, all can be called our service. Which devices? Besides the mentioned firewalls, NAT, RPS, load balancers, and what else? For example, things like WAF, anti-DDoS, Bastion hosts. all of these can be called a part of our service called service. In terms of service delivery, when linked together, they actually form these devices. So what does chain mean, right? This is referred to as a chain, right? Actually, chain is easier to understand when you think of it like a bicycle chain, right? The word itself is chain. This chain refers to linking all these aforementioned components together, allowing your traffic to sequentially pass through one by one in one go. This is called a service chain. The abbreviation is SFC. Looking at its definition, it provides ordered services for the application layer, simply layers 4 to 7. What does ordered service mean? It means letting your business traffic pass through these service boundaries, one by one, which are the endpoints of our service function. Then afterwards, actually, it just explains what was mentioned before. So this session mainly covers these two topics, which are very, very common in our data centers. Let's first understand what micro-segmentation is. Let's start with the basic concepts. Well, our micro-segmentation and service chains. Let's first understand what micro-segmentation is. Let's start with the basic concepts. As for the basic concept, this has already been mentioned in VXLAN. Within data centers, the need for business isolation is very widespread. In traditional subnets or traditional business environments, which includes traditional data centers and our traditional enterprise networks, we use business subnets with ACLs to achieve isolation. However, we know there are definitely some problems with this approach, such as if we use VNR or VLAN for isolation, achieving isolation, but you can't isolate within a single subnet. Traditional networks do have a way to accomplish this. Everyone think about how to do this. That is, in traditional networks, to isolate within a subnet, you need to enable port isolation on all ports, and then on the gateway side, enable something called ARP, Local Proxy Enable, which acts as an ARP proxy for the same subnet. This way, intra-subnet visits, because the layer 2 switch has enabled port isolation, all layer 2 traffic will be routed to the gateway, and at the gateway, another ACL is implemented. Thus, all layer 2 intervisit traffic will be directed to the gateway, and at the gateway, another ACL will be implemented. Ultimately, ACLs are still being used, and you will find that your ACL has become very, very detailed. Your ACL should match this 32-bit host address. This actually adds some complexity to your configuration. So what can be done? If the traditional method doesn't work, then we need to find another way. Maybe still using ACLs, but my ACL match will not be just a 32-bit host address anymore. Instead, it will match something else that can identify the target host. What could it be? In the definition of microsegmentation, this V could be something you might consider. Take a look. IP addresses, IP subnets, MAC. These still fall within the range of what a regular ACL can match. You can check. ACLs can match IP addresses, can match subnets. Even these called layer 2 ACLs, which should start with the number 6000 called MAC, called layer 2 ACLs. They can match MAC addresses, and in our layer 2 data, the type field and length within the layer 2 data should also be matchable. But these later ones, they can't be matched. The name of the VM, the name of the container, the type of operating system, all can be used for matching. This is somewhat similar to what? If you've worked with devices in enterprise networks that perform what's called application recognition, which may be in the security domain, you'll find that these devices can base their matches on the name of your host, or say your computer, right? What SOGO it logged into, for instance, an account of some software, an account of some SOGO input method, an account of WeChat, and use these as characteristics to match your computer, then convert you into a user. Well, what can vMatch? We've already mentioned that. What comes next? It's that one characteristic, or say you share a common characteristic, like you all logged into WeChat, or say you all have operating systems that are Windows 10. Then you will be segmented into a group, and what happens next is just like with ACLs. Between segments, I execute the corresponding filtering policy. This is called micro-segmentation. So, micro-segmentation is a finely grained security isolation technology. This security isolation, simply put, is like ACLs, determining whether they can access each other. It follows certain rules, which we've mentioned earlier. What are these rules? Take a look, for example, the names of our virtual machines, the types of operating systems of the virtual machines, all these can be used. Through this, we can isolate business services from each other within the VXLAN network. Why within the VXLAN network? Here we must mention a new term, which is in the VXLAN network. This leads us to mention a new term called an EPG. EPG. What is an EPG? An EPG is what we use in micro-segmentation. Actually, micro-segmentation, you could say. That segment is called micro-segmentation. It's a definition. In reality, it has a specific term called an EPG. EPG stands for endpoint group, which means a grouping of endpoints. Basically, it's about grouping servers or virtual machines that have similar characteristics into one group. This is called an EPG. What we need to do is define policies between these groups. Within groups, we define the policies. The actions, take a look, are still only permit or deny. This has also been given a term called group-based policy, called based on group these policies. Everyone, take a look. With the ACR approach, you'll understand it. There's nothing particularly new. So why this EPG? Why would it be specifically mentioned in a VXLAN network? Because in our EPG, it supports, think about it, traditional ACLs, right? Only support on a single device to execute. Traffic enters here and exits there. When it enters a device, then we will inside this device determine how to execute. But in VXLAN, think about it. Isn't the traffic possibly going from one of our leaf nodes entering? And when exiting, it exits from another node. It goes through a VXLAN virtual overlay network. Then it involves a question of which device to execute on. This microsegmentation is policy execution. This GPP, our GPP, where is it executed? It needs to involve in the VXLAN network to transmit this packet information. Like, for instance, if I execute here, then wouldn't I, on my side, the sender of the message need to, in the VXLAN message, pass through a field, its source EPG to carry its source EPG? What is it that carries to the other end, where the other side, based on seeing what the source EPG is and what the destination EPG is, looks at its local policy matrix, which is its local GPP configuration. That's why, in the VXLAN network, we need to specifically mention it. Okay, next let's look at our definition of an EPG, called an endpoint group. It actually is capable, based on many characteristics, of classifying. So, according to our definition, we can classify our EPG into different categories. For example, the first one is if you haven't assigned it to a group, it's as if it hasn't matched any group, called an unknown group member, not belonging to any group. Group members, as you can understand, are just those who have been assigned. And then, within group members, different group members, you should know what that means by the name. For example, if 56 is ungrouped, and 34 then belongs to all 1234 are group members. If we consider in-group members, 12 belong to in-group members, 34 belong to in-group members. Then different groups, for instance, in-group members would be 12 belonging to one group and 34 to another group. As for different groups, for example, 23 belongs to different groups, 14 belongs to different groups. Try to understand this with the concept of ACLs. Another concept is policy-based, group-based policy, a policy based on groups. That is, my policy now is based on between these groups to be defined. So I can target this group 1, group 2, and define a policy between them. At the same time, it's ungrouped and grouped situation. I can also define a policy, and for between groups, that is within the group, they are by default either accessible or not. I can also define this policy so we can see our current policy, what types it includes. The first one from left to right, we'll look at them one by one. The first one, within the group, we can define Simultaneously between groups we can define unknown group, and this group we can also define. So let's take a look. We have several definitions. Which policies are these types? So by default, these situations, these types of policies, do they have a default behavior? It's like this. What has a default behavior? Think, for instance, when you do MET, in the case of MET, this action, does it have this default behavior? This action, does it have this default behavior? It's the same, just get to know it. Why? Because we only need to understand a bit. That is, for different switch models, your default grouping, default policies, just like the 3 examples above, its default policy is different. So you just need to understand a bit. That is, for these few types of policies, different device models might have different default behaviors. You can check this in the product manual for the model. It will guide you, like for instance, regarding within group, what its access policy is. Here we are just giving an example. This example just lets everyone see a possible default situation. Like a possible situation is unknown group members. It's as if between unknown groups between 5 and 6, it is permit, then unknown group and known group. That's like 5, 6, and 3, 4, 1, 2. It defaults also to allow mutual access at the same time. Group members such as 1 and 2, 3, and 4, between them by default is deny. And at the same time, across groups, that is across these groups, between 1 and 2, it defaults also to a deny. So this is our micro-segmentation. The application scenarios of micro-segmentation, actually everyone can think about it, it's quite simple. Different virtual machines, although they are the same from our user's perspective, this user might be in, let's say, our public sector or in our private sector, deploying different virtual machines within one subnet. But these virtual machines might have different purposes. For example, one might be a business server, while another might be their remote work terminal. In that case, if they do not wish to access each other, since they are in the same subnet, this is normal because perhaps for this tenant, only one subnet was allocated. So, they cannot simply use different tenants or different subnets to route through a firewall on the firewall side to control the policies between different subnets. What can they do if it's not possible? In the same subnet, we can use micro-segmentation to restrict access within the same enclosure, preventing them from accessing each other. How is this done? We could say it's on our C1 switch, manually configured, or what else? Or on our switch, if it is managed by our controller, we could also on our controller with just a few clicks of the mouse, complete this operation, but we need to understand what the principle is behind it. Also, if I remember correctly, how it is implemented. I'll show you shortly. When we look at this configuration, we'll mention again the working principle, and then we'll see this setup. Let me remind you about the working principle. Let's take a look. First of all, look at the simpler one, local forwarding, which is this traffic control on a single device, source and destination on one device. Everyone, look at virtual machine 1, virtual machine 2, subnet respectively 10.1 and 10.2. They can see they are already divided into different groups. So this packet enters our leaf 1, where leaf 1 has already been configured with this group and the policies between groups. Upon receiving the packet, it checks to examine the packet. How to check depends on what conditions and characteristics you use to match the packet. Anyway, it will check, and upon checking, it finds that the source IP belongs to this group domain. Then it checks the destination IP. When checking the destination IP, pay attention. It probably first looked up the routing table, or maybe first the layer 2 forwarding table. To see this packet, its destination, whether it is local. If it is local, it's directly forwarded through a layer 3 or layer 2 switch. It checks this EPG group locally. If the destination IP, once it checks, it finds that it needs to go through VXLAN to be thrown to another leaf, it locally does not check who the destination EPG is, because in VXLAN, under this scenario, the design rules are based on the destination, this outbound direction. The rules are designed for that particular direction, called V-type devices, to perform this actual policy execution. So in this VXLAN scenario, if the destination IP is on a remote V-type, it will not locally check what the EPG group is. Now let's return to our local scenario. So everyone can see that the destination IP is actually local. So locally, it will check this EPG group. After obtaining the EPG group information for source and destination, it will perform a GPB check. Then, looking at the policy deny, locally, just kill it. So, on the third layer, we just mentioned if it's across 3 layers, then it's performed on the destination V-type. The GPB policy execution on the destination device will address an issue. So, say on leaf 2, isn't it leaf 2 going to check its source IP again? Well, let's assume this is based on this source IP to classify this EPG group. Of course, this is just for ease of understanding, but you could also say based on the operating system type. For example, VM1 is Windows, VM3 is Linux. Then between them, based on the operating system type, you can also build groups. This is just to help everyone understand. It's not that microsegmentation is the same as our traditional ACLs, only based on this IP to make divisions. It's not. Then back to our question. After leaf 2 receives it, will it check again by itself which group the source IP belongs to? Actually, there's no need, because in our VXLAN scenario, our source VM and destination VM are not on the same device. The source VM belongs to which EPG group this source is. This equals with type, it will check. And after checking, it will take this EPG information. Everyone, pay attention. EPG information, actually, it should be uniform across the network. Uniform across the network, meaning on both leaf 1 and leaf 2 sides. Because you think leaf 2 has to configure a policy. In configuring a policy, it implies that on the leaf 2 side, it actually knows that such an EPG group exists. And this EPG group has a corresponding ID number. This ID number on the leaf 1 side, once recognized, it finds this out is not coming out from my side. It is going out at a remote V-type. So it will carry this EPG group corresponding number, place it inside the VXLAN packet, carry it to leaf 2. After leaf 2 receives it, it will only check this destination, this called EPG, which one it is. Then based on the VXLAN packet, carrying this EP, that is this ID, to match which EPG group it belongs to, then directly execute the action, so everyone will see which field in VXLAN, as I mentioned earlier, besides VND are all reserved fields. So, it's through a reserved field that contains something called a global policy ID. That carries the EPG group number. Pay attention, this is just a group number, not a group name. Effectively, on a global scale, we have a group number and its corresponding name. So, let's look at the layer 3 forwarding scenario. It's across devices from this ingress V-type to our ingress V-type, in between, how it transfers. Let's look, starting with the first. VM1 sends the packet to leaf 1, and leaf 1 will locally check its associated EPG to see which EPG group the source belongs to, then sends a VXLAN encapsulation, and also includes the source, that is, the EPG ID, written into the VXLAN packet. After leaf 2 receives it, it will then, based on the destination IP, check the corresponding EPG group. Once identified, now the source, carried in the VXLAN packet, destination I've checked locally, then check my policy to decide how to proceed. Thus implementing, let's take a simple look at this configuration. There are 2 methods. One is based on command line configuration, and the other is based on controller configuration. First, let's take a look at some configurations that are essentially what we need to do as basic setups with microsegmentation, which are not very closely related to its own business configuration. We can take a look. Starting with the first, we need to configure our system resource mode to include ACL in the UFT flexible resource mode. This means configuring system resource UFT hybrid ACL. Then we go on to allocate our ACL tables UFT flexible resource mode to our microsegmentation service, which is to assign full forward ACL resource EPG. Then we use our segmentable function, which is traffic segment enable. Afterwards, we configure the default behavior between groups. We've said before that it has default behaviors. You don't have to configure it, but you can manually do it for things like unknown segment, default policy, and same segment, as well as between segments. We can also do this and show everyone just the default groups, which are microsegments, and then members within can also be configured for default policy. Next, let's look at how we create our EPG groups and how we add this group. When adding, we take a look inside our group, which is within the group. And this is between groups, all of which can be set to a default behavior. Then let's see how we create our EPG groups and how we add this group into the system. When adding, let's look at how to first create a segment, which is our traffic segment ID. Notice there's a concept of change, and it also has a name. Then afterwards, we add this address into our system. If created manually, then you can add it using an address. Afterward, it's a bit like our MQC. We need to create a classifier, assign it a name, then rule permit source segment and our destination segment. We have to configure all of these, then set up our segment behavior, which involves configuring what exactly it will be, whether it's a permit or a deny. Afterward, we need to configure our policy, link this classifier with our behavior, similar to how we configure MQC. A simple case to look at mirrors our MQC configuration methods. Let's briefly look at an example, a simple case to help everyone understand how to manually configure. In our example, we have VM1 and VM2, along with two physical servers. They each belong to EPG1, meaning VM1, and VM2 belong to EPG1, while the physical server and database server belong to different EPGs. Let's look at their requirements. VM1 and VM2's physical server can access the database server. However, VM1 and the physical server, VM2, and the physical server should not be able to access each other. That is, EPG1 and the physical servers shouldn't be able to interact. So, we need to define that they should not interact between groups, but VM1 and VM2 can interact. Therefore, we must define that they cannot interact between groups. That is, within the group, its policy also allows for mutual access. This should belong to, say, EPG3, right? So we should define that our EPG1 and EPG2 can access our EPG3. So let's look at what we need to do now. First, the first step is to divide the groups. After dividing the groups, what we need to do is allow VM1 and VM2's group to access VM3. However, VM1's group should not be able to access VM2. At the same time, for intergroup policies, they should be set to default allow. Now let's look at the basic configurations first, which involve setting up our resource mode. CE switches have many configurations, including when you set up VXLAN, such as if you need to configure RRB type forwarding. You have to configure the table to be a layer 3 table, which means that the resources are fixed, and you can configure them to store more layer 2 tables, or to allow more storage of layer 3 tables. This place is just an extra mention to help everyone understand the CE switch often has configurations regarding table resources. Back to the main topic. After configuring these basics, we need to turn on our traffic segment enable, and remember, the default policy for unknown EPG groups is permit, which doesn't really matter because it doesn't involve unknown groups. But what we need to do is set the default policy for formed groups to be a deny. Then, essentially, we just need to allow access between 1 and 3. Okay, let's take a look at adding our EPG groups next. Specifically on leaf 1, grouping VM1 and VM2 together. Remember, it has a number. Okay, let's look at what comes next. Adding our EPG group, specifically on leaf 1, adding VM1 and VM2 to one group. Remember, it has a number. The following steps are similar on our leaf 1. We need to define this classifier, that is, from our original group to the target group to create a classifier. Then afterwards, for these groups 2 and 3, we also need to create a classifier. Next, we create a behavior, which we can examine. They adopt our default behavior. Now let's look at how our controller orchestrates, how it performs orchestration. During controller orchestration, it actually can be said to orchestrate through the controller in a more detailed manner. We can match based on many of our characteristics. Now, looking at controller orchestration, it brings up some concepts which might be somewhat advanced now, as in our public cloud, we introduce a concept of VPC, which you can understand as essentially a tenant or something like that. Or you can understand a VPC as like what we discussed a few days ago about VXLAN, a VRF. This is a VPC. A VPC can be understood as under one VPC having different routers. This router can be understood as being our different layer 3 devices under which there might be different sites. The requirements are still similar. We can take a look at the same source and destination EPG between. That is within one EPG. We can say it's defensive behavior. We can define for the same switch under different subnets. We can define different EPGs, define their defensive behavior between for different switches, but under the same router. We can also define, so when we configure on the controller, we can configure based on our IP address, MAC address, hostname, etc., to set up our source and destination EPG. Now let's look at our deployment case, which is based on different subnets for our isolation. Let's consider this scenario, translating the source within a VPC, performing a translation within a VRF. If we want to achieve isolation between two VMs without relying on a firewall, we can use micro-segmentation technology. Divide VRM1 and VRM2 into different EPGs, then create a policy. Let's consider this configuration approach. Some earlier steps, just be aware of them because they are not yet relevant. Like steps 1, 2, and 3, steps 4 and 5, what we really care about are steps 6 and 7, and our step 8. First, let's consider the key configurations. On the controller, we can create our EPG in the network application. Take a look. Within this EPG, we can add our EPG by what? On this layer, we can see many options like virtual machine names, those addresses, belonging to which host machine, all can be added. Moving forward, let's take a look. Orchestration is very simple. Just drag a source EPG over, then pull a destination EPG over, and in between create our business chain, look at our policy, whether they can access each other or not. That's our micro-segmentation, which can be expanded upon. Let's mention how micro-segmentation is implemented, whether there is a service brother present or not. About micro-segmentation, in the previous configurations, was its essence seen? That's micro-segmentation. It was in our previous configurations. Was its nature observed? Still based on ACL, because we see it has a configuration command. Where is it exactly? Let's look at this place called assign for ACL resource EPG mode. There's an issue here. The essence of it, although we can base it on our host name, for example, based on our virtual machine name, based on MAC address, or based on the host to do traffic segmentation. Then at the bottom layer, your ultimate filtering, is it still done by the hardware switch? Or that hardware switch ACL, we know it's wired, its QACL is wired, we know our ACL is what we see from the command line perspective. Then from the hardware perspective, it's called hardware ACL or QACL. Different manufacturers might call it differently, or it's done through something related to TCAM. Here's a problem. When I implement microsegmentation, let's say my microsegmentation is, let me think about my microsegmentation. For instance, I defined, say, an EPG. I defined from one EPG1 to access EPG2. Everyone knows this EPG actually can't be used as a standard for traffic matching at the bottom layer. Your traffic at the bottom layer is still matched according to the binary of the packet, relevant information in memory, just directly checking and matching this packet, like within this EPG, right? Although on my controller, I seem to have configured only one rule, a rule from EPG1 to EPG2. Is it deny or permit? Assume on my side of EPG1 there are 100. My matching virtual machines, EPG2 again has 100. Think about it, actually, when our instructions are issued at the bottom layer, if it still goes to first do this matching, check which traffic it belongs to. When the commands are issued at the lower levels, we look at which group the traffic belongs to. After my EPG is implemented, what could the issue table look like? Guess what? What have I actually issued at the bottom level a single rule or 10,000 rules? Has anyone thought about this problem or has anyone encountered it in service? What exactly is it? Actually, this question is very interesting. When we discuss micro-segmentation, we say it's very convenient and useful. But when it really involves switch hardware tables, you need to consider one thing. What is really issued in the hardware table? 1 rule or 10,000 rules? The difference is significant. And I've taken the example of one EPG to another EPG. What if in a network, I have one EPG to 4 EPGs? Let's assume I have one EPG to 4 EPGs. Suppose between these 4 EPGs, there might only be one EPG inside each. So there are 4 on this side, but still 100 on the other side. Our IP addresses, for instance, or our virtual machines inside, there are still 400 rules. 400 rules versus 4 rules. The representation in the underlying layer differs greatly. So what is the answer? The answer depends on the manufacturer's implementation. What we should do now is what we can achieve when we look up in hardware. It's not just about issuing. It's not just about this. It's members, for instance. We take these members as a basis for lookup. We can base this on our proprietary chips, in which we look at the EPG table. Essentially, we do a lookup first. After the lookup, then go map this to the EPG table. What's issued at the hardware layer is from EPG to EPG. So our presentation specification is very simple. But why bring this up? Because some of our competitors, for instance, competitor CG, their current implementation is still, regardless of what I set up on top, maybe from one EPG to another EPG, what they distribute at the base level still depends on the ACL inside, so they dispatch the real hardware ACL based on that match. And their resource usage is terrifying, so you will discover competitors might in the scenario of EPG. Their controller simply doesn't encourage you to use EPG, doesn't recommend using micro-segmentation, because their presentation specification can't handle it. Because when you actually use this requirement, you may find the EPG rules. I wrote 5 rules, but there are a lot of endpoints inside. So in the end, their ACL presentation just isn't enough. So this problem is about the service. If you have encountered it before, you might want to look into it. This just varies by manufacturer. Their implementation is different. Whether they recommend this function or not varies. It all depends on your base implementation. Okay, let's take a brief look next at our business chain. What is a business chain? Actually, I mentioned it at the very beginning. That is in our data center, your traffic that might come from one of our virtual machines to another virtual machine, or from our virtual machine accessing the external network. You might need to go through many security devices, and these security devices, we call them in the telecom industry, named a service. That is what we call them, called a service. That's what we call it, just our service. What do we call it? It's called our service. What is it called? The service. It's called a value-added service, also known as a WAS device. So these WAS devices, what are they called? On our business chain, they are called WAS devices. So the WAS devices in traditional data centers, or rather not just traditional data centers, but in traditional enterprise networks, those who have experienced it will know the way we should arrange it. Either it's strung inside, right? Or it's hung alongside the core, above the core by using a diversion method to let the traffic pass through sequentially, like this, right? To implement our PBR, making the traffic detour when it comes in, and then after it rounds from this side, it matches again, and then rounds from this side again. This is done through possibly different VP instances, going back and forth, back and forth. This is one way of implementation, which is centralized. Hung alongside our span accumulation is a traditional data center. Implementation, including some private clouds, might still do it this way, but often what we do, actually, inside data centers, you will find it's not so easy to do. Why? Because in data centers, it might sometimes, especially in the case of public clouds, for private clouds, they might still use high-performance modular devices to do this. WAS devices on these modular devices might perform a VCS. For instance, take this diagram as an example. For instance, on the span accumulation side, I might hang a very high-performance modular device. On this rack-mounted device, I might have created many VCSs. each VCS corresponds to a tenant, that is, corresponds to a VRF. Let's return to that concept inside the data center, right? For tenants, it's divided into VRFs. So if the VRF needs to interface with our firewall, it definitely hopes that the traffic on the firewall remains isolated. Therefore, on the firewall side, there is a concept called VCS to perform isolation. However, there is now also a concept called NVF, known as VFN. VFN stands for Virtual Network Function. This might not be a hardware device, not a rack-mounted device. It continues with many of our so-called VCS or similar. It might just be on a physical server. Then it has installed something like our search system through this software to achieve a corresponding function, such as a virtual IPS, including our firewalls. Huawei's firewalls now also include our USG6000V to implement this VFN, including many devices are doing this. What's the advantage? The advantage is it's very convenient for scaling up, right? If I feel the performance is insufficient, I just add another server. On this server, continue to create some of our WAS devices, and this is a real scenario used in the public cloud. At this time, you'll find that the location of its equipment might not be fixed. If we say, you will notice that the location of the devices might be variable. At this time, if you still want to implement PBR, you will find that manually configuring this PBR would be too complicated. The device might not be locatable, and then the traffic, if diverted, would be very, very troublesome. So what do? We introduced a concept called our SFC. SFC can achieve what kind of effect? It will assign identifiers to these WAS devices to define a number. Then, at the controller level, pay attention, it's at the controller level. When doing orchestration, you just need to pull which service device to pass through first, then which one next. Sort them like this, line them up, and then line up the traffic. Which source, then which destination. Between source and destination, when I want to make this interaction, I pull it through the middle, for instance, on the network, or pull an RPS, pull like this, these middle nodes, then it is WAS. Then this traffic will automatically help you sequentially access these WAS devices. How is this done? Let's take a look at some basic concepts. Later we will see how it's implemented. There are many basic concepts. Essentially speaking, it's still the same few things, only that they've been given a term, the basic concept, called SFC. What is SFC? Service function chain, right? It's like this domain, you can understand it as VXLAN has its domain, SFC has its domain. What does this domain mean? Traffic comes in here, you enter this door, then I categorize you, you're considered within the SFC domain. EPG, we talked about it before, it's about categorization, making a group called EPG, classifier. What is a classifier? After the traffic comes in, which business chain do you belong to? We mentioned before, you need to pull a chain here, right? Which chain do you belong to? I pull it through the classifier SC, service classify, which is at the boundary entrance of this domain. After you come in, I categorize you, put a tag on you, right? After tagging, which chain you belong to. Then afterwards, no matter what, then afterwards I have set up the configurations throughout this domain. What is this configuration? That is how this chain should forward. What are the service nodes? Service nodes are on this chain, right? There are many service nodes. So number 1, number 2, number 3. After you come to me, I first see which chain you belong to. Then, based on that, I proceed with the processing. And then see where you are now in this chain, the first node, the second node, or the third node. Then decide, now that you're here, you belong to this chain. And then at this point, you've already passed through 2 nodes. Next, you should go to the third node. I'll then direct you to the third node. This is called service node, called service function, which are our WAS devices. So what is a business chain forwarding node? It's like our service leaf span. So it is responsible for routing your packet to SF, to our what we call value-added service devices. So it's called business chain, forwarding node called service function forwarder. Then the business chain path we talked about before, right? The message path, it's called a service function path. That is when you're transferring the message which path do you belong to now? You can understand it as we're now talking about this SFC, right? Saying this, C is a chain, a link, and this chain actually refers to SFP called service function path. There are many application scenarios. Actually, there are two main types, one of which is inter-VM communication, for instance, VM1 accessing VM2. I hope to do more than just simple access capability. I also want to perform an IPS security check, set up a firewall, such as NAT configuration, or implement LB load balancing. This is our first scenario between VMs. The second scenario is external networks, like going to the public internet, or the public network wanting to connect to our internal network. Then I might involve LB devices, because external access to internal traffic might first go through LB. LB might be responsible for balancing to many service endpoints. Then let's mention our SFC, right? Is a concept at the controller level on our controller. How is it implemented at the forwarding layer? Let's take a look now, combining what we just discussed, those concepts. What is SS, SFF? What is SF? What is SC? Let's look at the implementation method. The first type of implementation is still PBR. No mistake. The first method is still PBR, only that this PBR is no longer traditional PBR. It combines our approach. The idea of this service chain, implementing PBR. Let's take a look. First of all, traffic enters the FC, right? It enters our SC, and in SC, it does traffic-based segmentation. After segmentation, it will send it to your next destination for forwarding. So pay attention. The controller on all nodes implements this PBR. So for example, after SC has divided, it sends to SF-F1 on SF1. There is also a redirection policy. It will decide based on the redirection policy where to transfer the packet next, and then to whom after that, transfer one by one. So you will find that the model of the service chain in the PBR method is not about manually configuring the PBR policy, but rather the controller automatically handles the routing forwarding for you, doing the PBR redirection. It will send it to your next destination for forwarding. So pay attention. The controller on all nodes implements this PBR. So for example, after SC has divided, it sends to SF-F1 on SF1. There is also a redirection policy. It will decide based on the redirection policy where to transfer the packet next, and then to whom after that, transfer one by one. So you will find that the model of the service chain in the PBR method is not about manually configuring the PBR policy, but rather the controller automatically handles the routing forwarding for you, doing the PBR redirection. However, this does not necessarily fully reflect what we talked about before, the concept of the service chain. So another concept, what is it? It's our NS8, which is another concept is our NS8. That is, it's about, we should note, pay attention, that in VXLAN within the packet header, an NSH header is inserted. This header, everyone should note, will record truly useful information. What does it record? It keeps track of which hop the packet is currently at within the service chain. That is, which hop you are at. It keeps a record of this, and it also records which service chain the packet belongs to. That is to say, on SC, right after categorization, within the VXLAN chain, a mark is made, informing the subsequent devices to which chain, which SFP it belongs. Everyone, note the SFP, which is actually what we call the service function chain inside that chain. After SFE receives it, it will check within the VXLAN chain header, that chain. Then SFE will look at which chain our packet currently belongs to, then check again which device on this chain it has reached. For instance, it sees now it's at the first device on the chain, then forwards to the first device. After processing by the first device, it sends back, and then it might change that ID to these devices, change the value, and after changing, forwards again. This forwarding process, after it's completed, it sends the packet to the next node in the chain. At the same time, you need to be aware of something. On all SFs, there's actually a correspondence. What correspondence? That is, which node and what its IP address is. It will look up the routing table based on this node number to determine that it's now forwarding to the third node. Then I need to find out what the IP of the third node is. It checks and then sends the packet to the third node. This is what we call NSH. This model actually aligns with the concept of service in our service chain. At the same time, our approach to traffic diversion is also divided into two types, known as NSH-AV and NSH-NAV. That is, NSH-AV means what exactly? It refers to our which devices, namely, our SF devices, support VXLAN packets. When a packet is sent to it, it carries a VXLAN packet. What if it doesn't support it? If it doesn't support, our SSF will strip off the VXLAN encapsulation. Then, after receiving it back, if unsupported, it's like our SSF will reapply the VXLAN encapsulation, then sends it back, after which it adds the encapsulation again. That's the two different approaches. So, not all these WES devices can support the passing of our VXLAN packets. Okay, as we've already mentioned, let's take another look at this aspect. Besides VXLAN networks, actually, within VLANs, it's also possible to examine the NSH header. However, in data center scenarios, right, NSH is definitely used more extensively within VXLAN. First, let's look at the process. The first step, a virtual machine sends out a packet to our SC. So SC, we say, it will classify the packet, and after classification, add an NSH header. What does this header carry? We said it first carries an SPR. This SPR is used to identify which SFP the packet belongs to, right? Which SFP, which pass. And at the same time, it carries an SR value. This value can be used as an index to tell the device which node it is currently at. So SC, right, when sending out, definitely the node is the first node. You can check what node it tells you it belongs to, is through a decrementing method, just one by one, reducing it. Let's look at the fourth step, reaching SF. At SF, once it arrives, first checks the SPR value. If the SPR value finds it's in path 10, then it searches within path 10, right? Then checks what the SR is, and then it determines the next steps based on the SR value. If the SR value is found to be unchanged, like I mentioned, at the first hop, go check what corresponds to the first hop device. It's found to be 1.1. Oh, configure 1.1. After 1.1 processes it, it might return it. After it returns it, you'll find that it carries the SPR value. Of course, this place is definitely what we call an NSH-aware scenario. If it's not, it might be a bit more complicated. It means it has to judge which chain the packet belongs to, our, called service chain. Then it looks again, the SR value decreases by 1. Look again, when it decreases by 1, it represents the second R54. The next one is which, then based on the preservation, then throw the packet to R54. This is an implementation of NSH. First, let's take a look, compare the service chain and WaveNet's similarities. Actually, if you talk about similarities, they both are meant to encapsulate packets. Only after encapsulation, the method of processing is different. One is to perform a type of traffic management between WS devices, right? The traffic goes in here, comes out here, and within it weaves in and out, right? Threading through. The other is simply and bluntly to create an isolation. You might understand that the purpose they achieve is somewhat similar but executed in distinct ways. Both are about artificially restricting access between traffic flows, introducing some artificial interference, but their methods of restriction are different. Okay, with that said, good. Thus far, this is our segment on microsegmentation and our service chain. It's a basic course content. Finally, let's quickly look at two questions. The first one, a true-false question about the microsegmentation feature of the CE series switches, is based on the source V-type, according to this policy, to control traffic on the packet. In this place, it's actually not precise, or it could be completely incorrect. because we haven't mentioned whether it's intra-switch forwarding or inter-switch forwarding. In the case of inter-switch forwarding, it's definitely on the destination side, right? Based on the GPB policy to control traffic. So this question is definitely wrong. Next, let's look at a description of microsegmentation. Which one is incorrect? The first one, it says under the scenario of local forwarding, source and destination VMs are on the same network device. Then EPG grouping is maintained on the same network device. There's no problem with that. The second one, about inter-device forwarding, the destination group number is written into the VXLAN packet. That's wrong. As we said, the destination group number is determined by the destination vtype itself. So that's wrong. Next, let's look at members within the same EPG group can directly communicate with each other, and there's no way to restrict that. They cannot communicate with each other. So it depends on the default behavior. Right, if you go with the default behavior, actually it's not to say that everything defaults to this. Firstly, look at the device model. Secondly, it's wrong to say it can't be limited. Furthermore, EPG is based on a traffic control model that includes EPG groups and protocol numbers, plus port numbers. It establishes a traffic control policy between groups within the group. In this case, actually, it's not entirely accurate, because we mentioned this, between groups within a group. That is also correct. In this case, it depends. If we're talking about controller products, then there are no issues with this. Okay, finally, let's summarize this course. That's about micro-segmentation. As we mentioned, the focus is on micro, right? Segmentation, the concept has been around for a while. It's just that this micro-segmentation is more granular than previous ACLs. It can be done based on containers, VM names, operating systems. As for the business chain, actually, in our public cloud, it's used more commonly. Everyone can take a look. In the public cloud, you buy one service, then you buy something like a firewall, buy an IP, and then back to the screen. The value-added services you buy, besides virtual machines, these value-added services, they are called a business. They will help you automatically link between these businesses. At the same time, in our private cloud scenario, often for the orchestration of this service, like having to pass through load balancing, or for security features, it will also go through our business chain. These two features are very much used in our current setup. One could say, even though it's different from IT, we still need to understand it. More often, you might actually perform it and know how the underlying business traffic model is specifically orchestrated. This might be covered in a later course, like chapter 17 might be discussed in detail, that it's business chain, for example, all at the lower level, like if through PBR, how this traffic is actually implemented, coming in from this side, then exiting from that side. This way, when we are orchestrating, if it's just controller deployment, then it's simple. But we need to understand what exactly this configuration does at the lower level. This is what we need to understand. Okay, thank you everyone. So all that was our today's two lessons, our principle of virtualization and our micro-segmentation and business chain. The principle of virtualization is to help everyone understand some basic knowledge, because later when we might be doing this operation still involves some basic operations. Then you might need a rough understanding of the principle. In some operations, you might say you won't be as confused. Of course, this doesn't involve too much, just the underlying logic, because if it's the underlying logic, it's probably all code implemented. We just need to know some basic concepts and know what each button and function means when you operate it. Micro-segmentation and business chains. Now we need to understand the basic concepts. In the subsequent courses, we will further discuss the implementation of specific traffic forwarding. This might be important for our DCN, data center network. We will cover it in more detail later. All right, thank you all for your participation. This concludes today's morning session and content. If you have any questions, please feel free to ask. We will continue in the afternoon to discuss more content. Please take a break. Thank you, everyone.